to today's lectures. In our last lectures, we have introduced the concept of vector space, subspace, and we have seen different types of subspaces of different vector spaces and their characteristics also. We have defined linear combination of vectors, and we also introduce a subspace which is basically collection of all possible linear combinations of subset of a vector space also. Now, let me slightly modify and introduce another terminology that is called linear span of a subset of a vector space. The linear span of a subspace of a vector space, it is basically, if you consider a vector space say V over the field capital F, let S be a subset of V, then the linear span of S is a set of all linear combinations of elements of finite sets of elements of capital S. So, that is basically linear span of S. So, this will be also a subspace. So, let us denote the linear span, I can denote as LS, linear span of say capital S as LS type. Okay. So, since it is a collection of all linear combinations of elements of finite sets of elements of capital S, so similar to my previous proof related to that collection of all the possible linear combinations of elements of a subset of a vector space as a subspace. So, here also it can easily show that LS is also a subspace of V. Since the reason is for any say alpha belongs to LS and beta also belongs to LS. So, let us consider alpha is equal to sigma something Ci star alpha I equal to say 1 to m, and beta equal to, let me consider sigma say something T star alpha or Tj alpha j, say j equal to 1 to say n, where your alpha I belongs to your capital S space and Ti as well as Ci belongs to the field capital F. Since I have already told that I do not want to write star frequently, so I will simply write down alpha is equal to sigma Ci alpha I and beta is equal to sigma Tj alpha j. Now, let C be any other constant, C be any other constant from capital F, then we have C times alpha plus beta. This is equal to, I can write down C times sigma Ci and alpha I, your I equal to 1 to m equal to 1 to m plus sigma, that is Tj, and alpha j equal to 1 to n. So, this is again a linear combinations of alpha 1, alpha 2, alpha j. If m is greater than n, then I can write down in a proper form, that is it is a LC of linear combination of alpha I also. This is equal to C into Ci plus Ti alpha I equal to 1 to m plus sigma Tj alpha j equal to m plus 1 to n if m is less than n. Okay. So, this implies that C alpha plus beta also belongs to LS place. So, implies, so it is a subspace of the vector space also. So, linear span of S is also subspace of the vector space V please. We are basically interested to generalize the concept of vector space by we want to also add the concept of dimension to the vector space also. Now, to assign a dimension concept to the vector space, let me introduce some more terminology please. The first is linearly dependent set. Let V be a vector space over a field say capital F. Let S be a subset of V. Then S is said to be a linearly dependent subset or set of V provided there are say n distinct element alpha 1, alpha 2, alpha n of capital S and n scalars C1, C2, Cn such that C1 alpha 1 plus C2 alpha 2 plus Cn alpha n equal to 0, where not all Ci are equal to 0. I mean to say there are some Ci which are also non-zero, but this relations holds good please. So, then I will say that the set capital S which is subset of the vector space V will be linearly independent subset of V, or we can say linearly dependent set of V please. Otherwise, S is said to be a linearly independent subset, set of V please. So, let us take some examples. So, let me consider a very simple vector space, say V equal to my F2, I mean set of space of all 2 tuples over the F please. So, we know this is a vector space and with respect to the standard vector addition and standard multiplication please. I have also already defined what do you mean by standard vector addition for Fn and standard scalar multiplication for Fn also. So, based on that V is a vector space. So, consider capital S consisting of the elements, say let me consider 1 0 and 0 1. Okay. So, I have to check whether this is a linearly independent or not. Now, we see for any linear combination, if I take, suppose it is linearly dependent, then there will be some C1 C2 such that suppose this is I have given as alpha 1, this is my alpha 2, then I will have basically C1 alpha 1 plus C2 alpha 2 will be equal to 0, where all Ci not equal to 0, means at least some Ci will be non-zero place. Let me check it. So, this means that I will have C1 into 1 0 plus C2 to 0 1, which is equal to C1 comma C2, which is equal to 0. 0 means 0 comma 0 is a vector coordinate place. So, this implies that these two vectors are equal if their corresponding component are equal place. So, this implies that C1 equal to 0 and C2 equal to 0 is the only solutions, the only solutions. So, your capital S is a linearly independent subset of V place. So, now onwards Li stands for linearly independent place. So, let me take some another examples. So, in my Euclidean space, this is basically the space is equal to say F3, which is I am writing as R3 over the when F is equal to capital R, a real line place. So, we know that V equal to R3 is also vector space with respect to standard vector addition and scalar multiplication over the real line R place. Now, V is equal to R3 and now B is equal to 1 1 0 1 0 1, another one is say 2 1 and 1. Now, let me quickly check whether this set F set is a linearly independent or dependent. B is a linearly independent or linearly dependent. Okay. So, we have suppose if I give the name, this is basically say alpha 1, this is my alpha 2, this is my alpha 3. If I give the name like this, we have here 1 into alpha 1 plus 1 into alpha 2 and minus alpha 3 equal to 0. Because alpha 1, if I add these two vectors alpha 1 alpha 2, I am getting basically alpha 3. So, this implies that B is a linearly dependent set of B place. So, one can also extend this is for the instead of R3, if I consider V is equal to say space of all n tuples place Fn, and if I consider B equal to say set of all the elements like E1 equal to 1 0 0 this one, E2 equal to 0 1 0 0 and EI equal to 0 0 and 1 at the ith place 0 and similarly En equal to 0 0 0 and 1. Okay. So, B is a subset of V. Now, you can immediately check that B is a linearly independent set of V place, because for any alpha belongs to V, alpha will be of the form of what? Alpha will be equal to something like x1, x2, something like xn type. Okay. So, it is the n tuple place. So, this implies one can write down for any linear combination of E1, E2 and En x1 alpha 1 plus x2 alpha 2 plus xn alpha n, and this is nothing, it will be, if you get see, it is basically x1, x2 and xn place. So, if I say that this is equal to 0, this implies that each xi equal to 0. So, B is a linearly independent subset place, linearly independent set of V place. So, we have understood what is the linearly independent and linearly dependent place. Now, let me introduce another terminology called the basis. Let V be a vector space over F. A subset B of V is said to be the basis of V, provided V is spanned by B and B is a linearly independent Li set or subset of V place. So, a subset of a vector space will be basis for the corresponding space, provided it span the space. I mean to say, linear span of B equal to V, L of B equal to V, and the B is a linearly independent subset of V place. So, for examples, V is equal to say Fn. We know the collection B is equal to say E1 equal to 1 0 0 and E2 equal to 0 1 0, this one, and then EI equal to, I will define already, 0 0 1, this is ith place, then 0 0, and then En equal to 0 0 0 and 1. So, if I consider this is a subset of the vector space V place, then I can immediately show that this will span your vector space V place. Okay. We know any element of V, say alpha, is of the form of your alpha will be equal to something like n tuples x1, x2 and xn type, okay, where xi belongs to the capital F place. Here I have taken capital F, again real number, you may take also complex, no problem please. Now, I see that alpha is equal to, I can write down same x1 E1 plus x2 E2 plus xn. So, this implies L of B equal to V. Now, only things I have to prove that it is a linearly independent. Sin B is a linearly independent subset of Fn. So, this implies B is a basis, the basis of V place. In fact, we used to say this is called the standard basis. It is called as standard basis in Fn place. Let V equal to set of all polynomial functions of degree less than equal to n and defined over the field capital F. We have also seen that capital V is a vector space also. Now, if I consider B equal to 1 x square x to the power n, which is a subset of V. Now, claim this B is a basis for V. So, to prove this is a basis for V, we have to show that it span V and it is also linearly independent. For any element P belongs to V implies that P will be of the form of P naught plus P1 x plus P2 x square plus Pn x to the power n. This is of this form please, where P naught, P1, Pi basically belongs to capital F please. So, this implies that this is nothing P naught. So, if I give the name, so this is my alpha 1, this is my alpha 2 and like this is my alpha n, this is basis. B consists of the basis alpha 1, alpha 2, alpha n, where alpha 1 is equal to 1, alpha 2 equal to x, alpha 3 is equal to x square and alpha n basically x to the power n, then I am able to write P as a, this is basically P 0. So, this will be alpha n plus 1 please. So, it will be basically P 0 alpha 1 plus P 1 alpha 2 plus like I can say P n alpha n plus 1. Okay. So, this implies that L of B, linear span of B is basically your capital B, I mean set of all polynomial function of degree less than or equal to n over f dash. Now, we have claimed B is a linearly independent subset of B. Suppose not, then I will have a linear combinations of these elements such that will be equal to 0, where at least some coefficient will be non-zero. So, let me consider say linear combinations, say A naught 1 plus A 1 x plus A 2 x square plus A n x to the power n equal to 0, such that this is true for all x, this is true for all x belongs to F please. But friends, as you know, this is a polynomial of degree n. So, it will have only n roots, means it will be 0 only at n places over the F. So, it cannot be equal to 0 for all F, since sigma ai x to the power I equal to 0 to n, okay, is a polynomial, of degree n. So, it has n roots, that is if I denote, that is if if I denote this is basically Px like this, that is P is 0 on the line capital F, if I say that F is a real number, please, is a real line, then it is then P is 0 on the line F at most at n distinct points. Okay. So, Px equal to 0 for all x belongs to F is not possible, is not possible. So, B is a basis of V, please. If you consider V is the set of all polynomial functions of finite degree over the capital F, then we will say that to span V we need a basis having infinite number of terms, please. So, let me define the concept of dimension, please. So, dimension of a vector space. Let V be a vector space over F and B be a basis of it. If B has finite number of elements, then V is called a finite dimensional vector space. Now, notes I will use this abbreviation FDV, vector space. Else it is called as an infinite dimensional vector space. So, we have seen then according to this definition Fn over F is a finite dimensional vector space and dimension is n. Set of polynomial functions of degree less than or equal to n is again a finite dimensional vector space of dimension n plus 1. But if I consider V with the space of all polynomial functions over F, then the dimension of this vector space will be infinite, because no finite linearly independent subset of the corresponding V cannot span the corresponding space, please. Okay. So, let me take some more other example, please, of the basis. Let P be an n cross n invertible matrix over capital F. Then all columns of P will be a basis of vector space V is equal to set of all n cross 1 column vector space. So, I am denoting that one as F n cross 1 type. So, this is we know again a vector space capital B. Now, I have considered P be an invertible matrix, claim that the columns of P form a basis for this corresponding space, please. So, this is again very straightforward, because first I have to show that it is linearly independent. So, let me consider P1, P2, Pn denote a first to nth columns of P, please. Suppose there is a linear combination of P1, P2, Pn which is equal to 0. Let x1 P1 plus x2 P2 plus xn Pn equal to 0. Then I have to prove that x1 equal to x2 equal to and xn equal to 0 is the only solution, please. You see, this is equal to 0, this means that I can write down this is your simply P matrix x equal to 0. I mean to say where P equal to P1, P2, Pn and capital X equal to x1, x2, xn transpose, please. So, this linear combinations of the P1, P2, Pn is nothing Px equal to 0. Since P is invertible, so P inverse exists, so P inverse Px equal to 0. So, this implies x equal to 0 is the only solutions, So, this implies that set B equal to P1 to Pn is a linearly independent set. Now, I have to show that it also span Fn cross 1s. So, let capital Y which is equal to y1, y2 and yn say this transpose, please. So, this is a column vector, please, which belongs to capital B. Claim there exists capital X such that Px which is equal to x1 P1 plus x2 P2 like that. Okay. So, this is equal to sigma xi pi I equal to 1 to n which is equal to capital Y. So, since Px equal to y, I have to know what is capital X. Now, P is invertible, multiplying P inverse to the both this side, I am getting capital X equal to simply P inverse y. So, we can immediately find out the corresponding n constant x1, x2, xn such that x1 into P1 plus x2 into P2 plus xn into Pn equal to capital Y. So, this means that okay, B span capital B also. Okay. So, I think we have given enough number of example of the basis, and now let me consider one more small results. It is like this theorem type. Let V be a finite dimensional vector space over capital F, or let V is spanned by finite number of elements say beta 1, beta 2 and beta m. Okay. Then any linearly independent subset of V is finite, right, and cannot exceed number of elements cannot exceed m. So, this is one nice results, looks like very obvious, but it proof is required pace. So, let me give very quick proof this one please. To prove this one will be sufficient if I somehow can show that any subset of V which contain more than m elements will be linearly dependent please. Let me prove it by contradictions. Suppose capital S equal to alpha 1, alpha 2, alpha n be a subset of capital V and n is greater than m and S is also linearly independent, also linearly independent. Suppose like this thing. Since beta 1, beta 2, beta n, I mean this set spans V. So, for each alpha j there exist m scalars, say Pij belongs to capital F such that alpha j equal to sigma Pij or beta I equal to 1 to m. Consider any linear combination of alpha 1 to alpha n as below, say x 1 alpha 1 plus x 2 alpha 2 plus x n alpha n. Okay. So, this is nothing, I can write again sigma x I alpha I equal to 1 to say n. So, this can be written as again sigma x I equal to 1 to n and each, okay, for sake of simplicity I can write j equal to 1 to n. Okay. So, it will be x j and this will be, I can write down j please. So, alpha j equal to this quantity. So, I will write down again Pij and beta I equal to 1 to m. So, this means that this sum can be written as, since it is a finite sum I can exchange this order please. So, I can write down here I equal to 1 to m and j equal to 1 to n, Pij and xj, then I can write down beta I please. Since P is a m cross n matrix, the m cross n matrix and m is strictly less than n. So, this implies P x, if I consider P x equal to 0 will have non-trivial solution. So, this means that there exists capital X equal to x1, x2, xn transpose such that capital X not equal to 0, but Px equal to 0. So, this implies that sigma xi alpha I equal to 1 to n, this is equal to I equal to 1 to m and j equal to 1 to n and p ij and xj, okay, this is into beta I. Now, so if I consider that x, I will have p1 1 x1 plus p1 2 x2 plus like this, you know, p1 n xn equal to 0. I will have like this and p m1 x1 plus p m2 x2 plus p mn xn equal to 0. So, I will have for this value capital X, this is equal to 0. This means that I am getting there exists x not equal to 0, but your sigma xi alpha I equal to 1 to n equal to 0. This implies S is a linearly dependent subset of V, please. So, for today it is all right. Up to this, we will continue in the next class. Thank you.